Oh, and also, you also writing.
Okay, I think we are ready to start. It's the very exciting moment now, and I'm gonna leave the word to Jessica Carter, the president of the APMP.
So yeah, I had the task to say welcome to you all on behalf of the Directive Committee or the APMP. And it's so wonderful to see all of you here for this conference, seventh conference of the APMP. And I'm not going to say very much more. I will give the word to one of the chairs of the Scientific Committee, Gemma Lorena.
I'm also not going to say very much. So I'll say welcome on behalf of the Scientific Committee. And the Scientific Committee, besides the three of us, also includes Javier Legri, who's somewhere in the audience, and Dirk Schlimm, who unfortunately could not be here. He's sick and was not able to attend. So part of my role in introducing this is to convey his regrets at not being able to come. I'll just remind you all, in addition to the invited keynotes that I hope we'll all attend in this room, there are around 60 talks over the next few days, and these are organized into quite exciting thematic sessions that are running in parallel. So please do your best working through the schedule to decide where to go. And then as a reminder to everyone speaking, please do keep to your time allotted so that people can attend all the talks that they plan to attend. The other two rooms are directly below this one and very easy to find. So hopefully navigation will not be an issue. To share some demographic statistics, about 60% of our speakers come from Europe, 25% from North America, 12% from South America, and 3% from Asia. The talks all went through a rigorous double-blind review process, and the abstracts promised to be quite excellent. And I'll also like to encourage everyone to consider attending the virtual online sessions that are also running in parallel as noted in the program. There have been some last-minute changes to the program, so the most up-to-date version is the one that is online. So if you're in a room and you're wondering why it doesn't match the paper version, I would encourage you to log on to the online version for the most accurate version. And I think that is all I was going to say. So I'll turn it back over to Sylvia.
Okay, so I'm also gonna be very brief. Basically, my task is just to make sure some organization issues are taken care of. And especially, I would like to really ask all chairs to be really strict with times, because it's a tight ship we are running here, and it's a big conference, so we want to be able to also navigate the parallel section smoothly. So please really be strict. We also printed these papers for each room, so there should be no problem. Also, I really want to thank the other members of the organizing committee who have done an excellent work here. And in particular, Guido Tana and Ludovica Conti, they are really the mastermind behind this organization and have been extremely helpful. Also, of course, my other colleagues, Andrea Sereni and Luca Zanetti, and the students, Nicolò Cambiaso, Francesca Doneda, and Tommaso Peripoli. Also, I want to thank Daniele Molinini and Valeria Giardino, who's unfortunately not here, for having worked on the program. So basically, that's it. And I'm going to leave the word again to Jessica to introduce our first keynote speaker. So thank you, everybody, for being here, and I hope you enjoy the conference.
Yes. Okay. So just a brief introduction before we continue with our first invited speaker. And I'm so delighted to introduce Karine Shemla as our first invited speaker of the APMP. Shemla has a long and impressive career with many remarkable contributions. She has for many years been a director at the CNRS, to our community very well-known research group Sphere and former RESEIS. She has a long list of awards and honors, and I cannot mention all of them. I can mention a few. I suppose she was one of the invited speakers at the International Congress for Mathematicians. She's been awarded the Otto Neugebauer Prize, as well as the Just Prize. She came to Paris to study pure mathematics, but after graduating, she got the opportunity to have a longer research stay in China, something I think maybe shaped the rest of her career. The visit paved the way for the history of mathematics in part, and in particular Chinese mathematics, and the contributions that have followed, in particular the monumental work, 9 chapters of on the mathematical arts, have made Shimla the capacity on Chinese mathematics. And although Shimla is the expert on Chinese mathematics, she has also contributed to many other areas in mathematics and history of mathematics. So one could mention one thing that is of interest to our community, her studies of mathematical practices, as well as mathematical cultures. But she also studied more recent history of mathematics, including the history of algebra, geometry, and arithmetic, something I think she will talk to us about today. So please, we're so happy to have you here.
Thanks a lot, dear Jessica. And I think we should begin with 2 disclaimers. The first one, I will not be brief. But for the second one, for once, and this came out of a discussion with Dirk Schlim, I will not speak about any sources, but I will speak about things on which I've been working for decades, that is the history of geometry. But before I begin, I want to thank the Association for the Philosophy of Mathematical Practice. It's really a great pleasure, an honor to be here and to share some thoughts with you. And I could not begin without thanking Sylvia, Ludovica, and Guido for all that they have done, for their wonderful hospitality. This was really heartwarming, and I really appreciated it a lot. They know what I talk about. Finally, what I want to present is partly based on joint work with Bruno Belost, with whom I am developing a project on Jean-Victor Poncelet, and in particular on Poncelet's contribution to the development of what was to become projective geometry. So what I would like to do in this talk is to highlight aspects of the context in which Poncelet put forward a key concept, a concept that would have a tremendous impact on mathematics, that is the concept of ideal elements. As I will show, the concept of ideal that was given pride of place in Poncelet's major work of 1822, to which I return shortly, this concept was the outcome of a reflection on the notion of figure, geometric figure. We will see that during the many years in which Poncelet carried out this reflection, he introduced another notion of ideality before settling on the one published in 1822. I intend to highlight that these developments took shape in the context of a specific mathematical practice in which Poncelet was participating, a practice characterized notably by an intertwining of philosophical and mathematical work. To be complete, I should also mention that this was intertwined with historical work, but this will play no part in the present talk. So the intertwining of mathematical.
Just to let you hear the end of the room, can I ask you to keep this one closer?
Please.
Thank you.
No problem. Is it better? Don't worry, I will repeat the main issue I have in mind. Thank you for the microphone. So the intertwining of mathematical and philosophical work in Poncelet's practice appears quite prominently precisely in the case of Poncelet's introduction of ideal elements. Why do I claim that Poncelet's concept of ideal elements had a tremendous impact on 19th century mathematics? The reason is that the concept, together with the philosophical reflections to which they were linked, part of this philosophical reflection, was appropriated in a completely different mathematical context by mathematicians who thereby achieved a major breakthrough and fulfilled the mathematical program on which they were working. And this breakthrough that was made possible by the appropriation of Poncelet's ideal elements is, I don't know how I achieved this, but it worked, Ernst Edward Kummer's introduction of ideal prime factors on a complex number. So you remember that Kummer introduced this notion, first introduced this notion in a letter to Leopold Kronecker on October 1845. And perhaps I should first make clear what Kummer meant by a complex number, because this is not our notion of complex number. For Kummer, he takes alpha, an imaginary root of the equation alpha to the power lambda equal 1, where lambda is a prime number, and he considers complex numbers as numbers of the form a plus a1 alpha plus a2 alpha square and so on, plus a lambda minus 1 alpha to the power lambda minus 1, where the ai are integers. And what he means by prime, as we will see shortly, is in a sense derived from ordinary arithmetic. So his intention, his project, his program is to develop an arithmetic for those complex numbers that is identical to the arithmetic of natural numbers of integers. So I have presented in front of several audiences already the idea that Kummer's introduction in 1845 of ideal prime factors in number theory was inspired by both Jean-Victor Poncelet's introduction of ideal elements into geometry and by Michel Charles' reconceptualization for them. In passing, I mentioned the fact that Charles was participating in the same kind of mathematical culture, in the same kind of intertwining between philosophical and mathematical work as Poncelet, but today I will almost not mention Charles. Whatever the case might be, clearly the use by Kummer of the term ideal comes from this context. So I have argued about this, and I will return partly to my argument in a moment. But what I would like to focus on today is this thesis, namely that ideal elements were introduced into geometry in the context of a practice of mathematics in which Poncelet participated and in which he shaped a new geometry. This practice, as I said, is characterized by an intertwining of mathematical and philosophical work. The conceptual outcome and part of the practice being appropriated as such and playing a key part in Kummer's innovation in number theory. So why do I claim that Poncelet's 1822 concept of ideal element was appropriated by Kummer? To evoke the arguments, I will focus on the first text in which Kummer presents his theory, which is a report with which he communicated his theory to the Berlin Academy in March 1846, the text being slightly revised before being republished in the following year in the Kreller Journal. Kummer starts his March 1846 article as follows: I have succeeded to complete and simplify the theory of the complex numbers that are made up of higher roots of the unity and so on. And I did this by introducing a specific type of imaginary divisors, which I call ideal complex numbers, and about which I allow myself to make a short communication. First, note the two epistemological values of simplicity and completeness, which we also encounter in Charles' work. Also note that the epithet imaginary is discarded to be replaced with ideal. Ideal, epithet of complex numbers, and later on we will see of divisors. We have here a practice of attributing terms to objects to which we will return because it's a practice that is similar to what we find in Poncelet's writings, not in Charles in this case. So we have here things that are divisors, and they are introduced in relation to other numbers that are complex numbers. Okay, so we have not ideal complex numbers in and of themselves, but we have ideal complex numbers that are introduced as divisors of actual complex numbers. I will return to the term actual shortly. So why does Kummer introduces this? It's because he noticed he has the project of, again, developing an arithmetic for these numbers parallel to the arithmetic of integers. And he noticed that for complex numbers of this kind, they can either be decomposed into factors of the same kind, complex numbers, or they cannot. In the first case, the number is composite, clear, whereas in the other, the number was until now called a complex prime number. However, I have noticed that even if f of alpha can in no way be decomposed into complex factors, it yet does not have the true nature of a complex prime number, because it usually lacks the first and most important property of prime numbers. So we have numbers who are not decomposable, but that do not have the nature, namely they lack a property. Property is something quite important in this context. And what is the property in question? The product of two prime numbers is not divisible by any prime number different from that. So this is what we should have if we had an arithmetic parallel to that of integers. But in the case of some numbers f of alpha, they have much more the nature of composite numbers, even though they are not decomposable into complex factors. The factors, claims Kummer, are consequently not actual. We cannot express them as f of alpha of the kind I have described to you, but ideal complex numbers. So in the first place, and this is the small letters that I will not read. In the first place, Kummer draws analogies between these ideal complex numbers and complex numbers that were introduced to decompose polynomials into their simplest factors, and so on and so on. But there is another analogy which he introduces when he turns to the constraints he has respected to deal with, to introduce the definition for these numbers. And this is where we see Kummer drawing a parallel between the ideal complex factors and ideal elements in geometry. So to achieve now a lasting definition, you see the point of the true, usually ideal. So we have true factors that can be either actual or ideal. Of the complex numbers, it was necessary to find out the properties of the prime factor of complex numbers that would persist, remain in all circumstances. Properties that would be absolutely independent of the contingency of whether the actual decomposition takes place or not. So to introduce a lasting definition, to introduce a definition that would hold for any factor, be the factor actual or ideal, he looks for a permanent property, a property that is shared by all these factors. And this is where he makes the comparison I'm interested in, more or less precisely like when in geometry, one speaks of the common chord to two circles, also when the circles do not intersect each other. One looks for an actual definition of this ideal common chord that fits for all situations of the circles. So you see, the purpose is to look for the correct definition, which will be based on a property that should be valid for any type of divisor. So this property will play a part in identifying divisibility of one factor of one number by a factor. And we see here a practice of definition on which I will not dwell, but which is a practice that in fact derives from Charles' rewriting of what Poncelet is doing here. But I have written this elsewhere. I don't want to dwell on this, but it's interesting that we have a practice of definition that is worth observing. So what we have is an analogy with geometry in relation to looking for a correct and a uniform definition, the same definition for any factor, and that the analogy with geometry is with properties that would persist in any circumstance of a drawing. And I would like you to observe here that in the same way as we had ideal prime factors, namely ideal being an epithet, we have here ideal common chords, ideal again being an epithet characterizing something which is a common chord. So the idea, I mean, the phrase ideal common chord and the idea evokes immediately Jean-Victor Poncelet, who introduced ideal common chords and ideal common seconds in his treatise of projective properties of figures in 1822. So okay, so what you have here is, I put two figures to illustrate the idea, the first idea of ideal common chords and ideal common sequence. I will return to what they are in a moment. To the right-hand side, you have two ellipses. Think of two circles if you prefer, that intersect in 2 points, and hence these 2 points define a line, which is a secant that is common to both of them. But the sequent also, the intersection are also the points KL, which define a segment which has a length and which is the common chord in this case. Poncelet wants to claim, and we will see how, that in the left diagram, we can still define a line, small n, that is a common secant to the 2 circles, the 2 ellipses. We can still define a line, and yet this line cuts the 2 circles, the 2 ellipses in imaginary points, and hence he will refer to this line as ideal common secant, whereas we have points m prime and n prime here, to which I will return in a moment, that are points on this common secant that are defining also a chord to which Poncelet will refer as an ideal common chord. So we see that he's using the same term secant, the same term chord, in the case to the left. So this is the practice of attributing terms that we find again in Kummer's practice. But this also refers to a practice with figures to which I will return. The point here is to have a generality in the terminology that refers uniformly to the situation of 2 conics, whether they intersect or whether they do not intersect. So I want to discount something. I want to discount a common interpretation of what the ideal elements in geometry were for Poncelet. So I want first to say what the ideal elements in geometry were not for Poncelet. Because to understand the parallel that Kummer is making and to understand the idea of ideality in both cases, it is really necessary to discard widespread and, I would claim, anachronistic ideas on this issue. And I think that what has happened is that David Hilbert has powerfully promoted a conception of a method of ideal elements that has been projected backwards onto Poncelet to the effect that one no longer understands what ideal elements are for Poncelet, and one hence cannot understand what the analogy Kummer does means. So I will pick up what Hilbert says about the method of ideal elements in Über das Unendliche, on the infinite. You remember that Hilbert first claims there are no infinitely small, infinitely large entities in physics, in contrast to what we have in mathematics, where one formula refers to an infinite number of assumptions. And he writes, we become acquainted with a completely different and quite unique interpretation, as well as a conception of the fundamental importance of the notion of infinity, using the extraordinarily important and fruitful method of ideal elements. So there is a relationship established between his reflection of the infinite and, the method of ideal elements. The method of ideal elements, he writes, finds applications already in the elementary plane geometry. There, the points and straight lines of the plane are originally the only real, actually existent objects. However, as a result, we have through 2 points, there is a line, but 2 lines do not always intersect in a single point. And it is well known that by introducing ideal elements, that is to say, for Hilbert, points at infinity and a straight line at infinity, one can make the theorem universally valid. So you see here, the first idea that elements that are ideal would be points at infinity and lines at infinity. And so real, actually existent objects, points of the plan, would be opposed to points at infinity that would be the ideal elements. And interestingly, it's the same epistemological concern as Kummer, the idea of making the theorem uniformly true. So these ideals may look like Kummer's, however, they are not at all what Poncelet means by ideal, and they are not at all what Kummer means as ideal. Hilbert interestingly goes on by saying another example of the use of ideal elements are the familiar complex imaginary magnitudes of algebra, so imaginary elements. And he adds, so we have infinite elements, imaginary elements, and he adds, just as in geometry, infinitely many straight lines, that is, those parallel to each other, are used to define an ideal point. So he bridges in this way the notion of ideal point with a notion of infinity. So in higher arithmetic, certain systems of infinitely many numbers are grouped together to define an arithmetic ideal. So here we note he refers to Dedekind's notion of ideal, which is quite different from Kummer's. But what is striking is that he is drawing a parallel between geometry and arithmetic. He is drawing a parallel, but this is not at all the parallel that we will find between Kummer and Poncelet. So to summarize, in geometry, ideal elements would be points at infinity, imaginary entities, and this is a widespread idea that one finds in many publications. However, I claim this is very different from what Poncelet means by ideal element. So let us turn to Poncelet's treatise of projective geometry. The key problem Poncelet faces is why is analysis, when it is applied to geometry, powerful, whereas geometry in the way of the ancients is not, and how to change geometry to make it as powerful as analysis. The key epistemological value that he has in mind when he thinks of the power of analysis is its generality, and he wants to implement generality into geometry. So he has two main principles: the principle of projection, which reflects the title projective properties. He focuses on properties that are kept through projection and we can then prove these properties on a particular configuration and claim them in a general configuration. This is the principle of projection. And a second principle, which is absolutely crucial for ideal elements, which is the principle of continuity, which will conclude from the general to other general states of the figures or particular state of the figure. So what the principle of continuity addresses the following issue: if algebra, analysis, computation applied to geometrical figures are powerful, this derives from the fact that they proceed through treating as same figures that ordinary geometry would treat as different. But somehow, Poncelet goes on, this works because these different geometrical figures can be treated as same. And hence his question, how can we modify the geometrical approach to figures to secure similar properties in geometry. So central to, and this, the principle of project continuity will play a key part in this. So central to this principle of continuity is the notion of a figure. He suggests considering an arbitrary figure in a position that is general and in a certain sense indeterminate among all those that the figure could take without violating the laws, the conditions, and the link that persists between the various parts of the system. So we have something here which is unclear. What are the laws, the conditions, the link that persist between the various parts of the system? It's really important to understand these terms, to understand what the notion of a figure is for Poncelet. We will return to these questions in a moment, but let me give you an example of a figure on which I will dwell. We have a conic section and a line MN. So an analytical approach would not distinguish between MN here, cutting the conic section in two real points, and a line N prime here, cutting the original ellipse in no real points. And hence, central for Poncelet's geometric approach of a figure will be the link that can be established between positions of a figure, if you want, the line cutting, the line not cutting, and also the link that will be established between properties of the figure in different states, in different positions, link established between a continuous motion leading from one to the other, the motion that draws the line MN to the position N prime, a motion through which, for him, relations would remain valid. Relations will continue to apply. And it's important to note that the principle of continuity is, and here I use the full phrase that Poncelet uses, is the principle or law of continuity of mathematical relations of the abstract and figurative magnitude. So you see that there is not only the continuous motion of the parts, but there is also the continuity of the law that define that give the mathematical relation between parts of the figure. And the point of the principle of continuity is, suppose one finds one or several relations of property of the figure using the ordinary explicit reasoning. The explicit reasoning is a reasoning that is based on parts of the figure that are real. This term comes from Carnot's geometry. If keeping the same data, one makes the figure vary by imperceptible degrees, and one applies to some parts of the figure a continuous motion. So you see this double meaning of continuity, the continuity of the law, the continuity of the motion. Then is it not obvious, Cauchy will have a lot to say about is it not obvious, that the properties and relation that one finds when found for the first system will remain valid, will continue to apply. These are two translations of the same term to which we can return for the successive state of the system, if, however, one pays attention to the particular changes and so forth and so on. So you prove your relation on a figure in a certain state where you can use explicit reasoning like the ancient geometry, and you state the conclusion to any position of this figure applied with this continuity, but which is not any type of continuity, because it will have to preserve the laws, the link, and the connection. That's what we have seen as the definition of a figure. So Let me, to explain what all this means, let me return to this example of a conic and a straight line. So, using the principle of continuity, Poncelet can claim that this line moved to M prime, continues to cut the conic in 2 points, even though these points are imaginary. These are the changes one has to make to the figure. Again, the principle of continuity implies that the chord is still there, and Poncelet draws, in fact, a supplementary conic to materialize the chord that was a real chord here, but has become another type of geometrical thing. I will return to this. So you begin to see that this figure that is drawn is not an ordinary figure of geometry, because it has elements in it that are not of the same kind. And this is where I return to the practice of figure. Indeed, Poncelet's geometric analysis of the figure goes one step further to the direction ML. Think of it simply as a direction, not as a line. That corresponds a diameter, which is a line that would cut all the chords drawn by lines parallel to MN, that would cut all the chords in their middle point. So we have O, the middle point of MN, C, the middle point of DE, Q, the middle point of QR, and so on. So this line exists. It's the diameter corresponding to the direction MN. And if we draw the tangents to the point M and N, we will find a point O prime, which satisfies with the point A, B, where the diameter cuts the conic, and the point O, this relation. Namely, we have a harmonic ratio between the 4 points A, O, B, O prime. And this is where we return to the issue of what an ideal element is for Poncelet. Indeed, he notices that it results from these definitions of the points O and O prime that these points can be constructed independently from the points M and N. And hence, they subsist in any possible case, even when the straight line is outside the curve. So we start, for instance, from M prime, N prime. It cuts the diameter in O prime, and we draw the tangent lines, and we have O. So any line gives rise to a point O or O prime that leads to the point, any line parallel to the direction M leads to a point O that leads to a point O prime, or leads to a point O prime that will lead to a point O. And these can be constructed absolutely independently because they are simply the middle point for one line, and hence the fourth point using the harmonic ratio. So what we see in Poncelet is that there exists between the lines MN and the line NN prime, as well as the point O and the point O prime, a very remarkable relation, which is such that when any of these things, the MN, O, M prime, N prime, O prime, any of these things given, the other three go by, exist automatically. So we have here the illustration of a law that should not be violated when we want the figure to be the same. And in particular, we do not want the line to continuously move to a direction that is not parallel. This is one of the things that should be maintained for the figure to remain the same. And as an illustration of what a link between the parts of the figure that we had in the definition of the figure, what a link might mean, I think that this is clarified by this claim that Poncelet makes about this figure. Since the points O and O prime considered as belonging to the line MN or to the line in the same direction of MN, these points subsist independently from the reality or the non-reality of the intersection M and N. There is no reason to neglect them in one case rather than the other, nor should this line, the line N prime, be neglected, since when it becomes exterior to the curve, it does not cease to maintain some dependence with the curve. And we have hence a symmetry between Mn and M prime and prime. We have a symmetry that is inscribed in the diagram that is determined by dependencies between these lines, which make it odd to consider that one should be a secant when it crosses the conic and one should not be, even though the crossing point of this secant with the diameter exists and can be constructed independently of the imaginary point. So there are things from the diagram that are real, even though they are related with other things through imaginary object. And this is precisely that for which Poncelet will introduce the epithet ideal. Assuming, he writes, that we do not wish to create new terms to designate the line MN and what belongs to it, and that we persist, you see again this persisting, in considering it as a secant when it ceases to meet it, we will say, in order to preserve the analogy between idea and language, that its point of intersection with the curve, M prime, N prime, and consequently the corresponding curve, are imaginary. That the secant itself is ideal. Indeed, it suffices to have the intersection O prime of this line in the direction of MN to have as a real point the point MN and to have the secant. The secant can be constructed even though it does not cut. So he refers to the secant that can be constructed, and this is the key concept. He refers to the secant that can be constructed as an ideal secant. It is not a real secant in the sense that it does not cut the conic in real point, but in imaginary point. The relationship with the conic has become imaginary, but the secant itself can be constructed, and hence it is considered as real. Elsewhere, Poncelet will tell that M prime, why are they not standing for ideal points, M prime and N prime, the extremities of the secant here? Because if they were constructed as ideal points, they should cross the conic, which they do not. So they cannot be constructed. We can feature them, but they cannot be constructed as points of intersection. And about N prime, Poncelet introduces the fact that they are ideal. It's an ideal cone in a fictive way. In fact, its length as a cone would be imaginary, but it can be constructed in a fictive way. And he introduces ideal to distinguish from entirely non-constructible straight lines in its path and direction, for which he would keep the term imaginary line. So when we have the parallel that Kummer is drawing between ideal factors and ideal common core, the key point is one can find a procedure to construct these factors, even though they cannot be expressed explicitly as complex numbers. Okay, so this is the key point, and you see that this is exactly the similar practice with constructibility and the similar practice with terminology. And hence, Poncelet distinguishes more generally between imaginary elements that could be entirely impossible, inconstructible in a figure that would derive from the primitive one by continuous motion. And he distinguishes imaginary and ideal, which refers to a specific mode of existence of an object which remains real in the transformation of the primitive diagram. The line remains real, but it ceases to depend in an absolute and real manner on other objects like the points that would define it. And hence we have, Poncelet goes on, since just as one already has in geometry names to express the various modes of existence that one wants to compare. So we have modes of existence that are infinitely small, infinitely large. Please remember that here he considers infinitely small, infinitely large as modes of existence. He introduces names to express modes of non-existence, namely imaginary or ideal, in order to give accuracy, precision to the language of geometric reasoning. So we have here a table of terms, and what is really interesting is that, in fact, if we look at Poncelet's publication of before 1820, in fact, they attest to a completely different use of the terms ideal and imaginary. And it seems that it was in 1820 that he introduces these terms ideal, imaginary in the sense that we have seen, and which completely differ what we have seen from what Hilbert introduced. So this is where he returns to, I'm quoting from a notebook he composed in the winter of 1818 and 1819, where he says, the use and routine of algebraic analysis have introduced into the ordinary language of geometry certain expressions which we call and characterize these beings of non-existence. And in this case, we are in 1818. What are the beings of non-existence? Infinitely large, infinitely small entities whose existence is purely hypothetical, but were introduced using algebraic analysis. What we do, he says, in 1880, what we do is that if we admit that two parallel straight lines meet at infinity, we ideally give an indefinite existence to their common point. So here, ideality refers to the fact that refers to the nature of the existence we give to objects like infinite points at infinity. And he goes on, the word infinite recalls the geometric non-existence of the object. It indicates that it assumes existence is purely ideal. The same thing with points, intersection points that have become imaginary. We maintain for these points an existence of sign, at least ideal. So you see that this Poncelet of 1818 is closer to what Hilbert understands with ideal elements, in contrast to the Poncelet of 1820, 1822. So what we have is, in this notebook, interestingly, just as one has names to express the various modes of existence that one wants to compare, this is exactly the sentence I read to you from 1822, before introducing ideal and imaginary in the later sense of the terms. Just that we are here in 1818, so this paragraph was taken almost verbatim. I will remind you in a moment. Just as one has names to express the various modes of existence that one wants to compare, one must have names to express the various modes of non-existence in order to give both accuracy and so on. So what is at stake here? We have a geometric figure, which is not the geometric figure of the ancient, but which is the geometric figure that one wants to introduce in order to ensure generality in geometry. And so this figure has elements that are not of the type one had in the ancient figure, but one has to think about what kind of elements one has in this figure to be able to work with the new figure. And he refers to this as the need to introduce metaphysical notion, because the metaphysical notion have their true source in the perseverance to apply the idea of continuity to a purely ideal state of a system. And hence, he calls for tracing a complete, faithful table of all the metaphysical notions that belong to the figurate magnitude. What does that mean? We have figures, and we need to understand what kind of elements we have in these new type of figures to be able to have a general geometry, not a geometry of the ancient. And as you know, this program is what he fulfilled when, with exactly the same introductory sentence in 1822, just as one already has in geometry names to express the various modes of existence and so on. But here we have a complete shift, a re-understanding of different modes of existence and different modes of non-existence. So we see that she had this project of analyzing the elements that enter in the making of a figure to have a completely general figure on which one could make general statements. And that the fulfillment of this program was the introduction of the opposition between imaginary and ideal, with completely new meanings with respect to what they had in 1819. So this is that to which Poncelet attests in the only published text that Kummer could read, or of which he hear about, namely the 1822 treatise. And this is that what Kummer has in mind when he thinks about picking up this notion of ideal elements into number theory, a notion of ideal elements that would ensure that a number be divisible uniformly into prime factors. Thank you very much.
Thank you, Karim. Can you hear me? Yeah. Good. We have lots of time for questions, so there are already lots of them.
So, thank you very much for a very interesting and instructive talk. And I would like to ask you to clarify slightly more the distinction between Hilbert's and Poncelet's concepts of ideal elements, because it seems to me that basically Hilbert did with Poncelet what Dedekind did to Kummer. That means that make an explicit algebraic construction that makes the fictive or conceptual ideal elements really graspable, and you can show and put them and calculate with them. So is it not just that if you translate Poncelet into algebraic equation, put their projective coordinates and complex numbers, so everything what Poncelet says is actually the same as Hilbert says in this framework of algebraic equations, complex numbers, and projective coordinates, so that in a sense, Poncelet is, so the relation of Poncelet and Hilbert would be that Poncelet has an implicit concept which Hilbert makes explicit. Or is there a factual difference where something would be ideal in the view of Poncelet, but Hilbert would not be able to grasp it, or something would be ideal in the Hilbert's concept and Poncelet would not be able to grasp. So is there a really factual difference, or it is just becoming more explicit?
There are factual differences because for Hilbert, points at infinity are ideal, whereas for Poncelet, in the Poncelet of 1820, 1822, points at infinity are not ideal. So this is a different notion. And what is really important is this opposition between what can be constructed, even though what it is partly imaginary, what cannot be constructed. And it is, in my view, this opposition that was taken up by Kummer when he introduced ideal divisors as divisors that can be constructed through the procedure with congruences that we know. And the key difference is that the key difference, for instance, between Kummer and Dedekind, excuse me one second. The key difference is that for Dedekind, the objects are ideals, all the objects, whereas for Kummer, we have actual numbers and ideal numbers. So we had a shift in the interpretation of what an ideal was, okay? And I don't think that with respect to the method of ideal elements, as I have presented it on the basis of Hilbert texts on the infinite, I don't think that you can make this bridge. But what is striking for me is that he's still making a parallel between the introduction of ideal elements in arithmetic and the introduction of ideal elements in geometry. There is, in the history, there is this gap, this German crossed my mind. In the history, there is this link, but not as Hilbert outlines it.
This is very stimulating. I have been from the very beginning of my training in algebraic geometry was exposed to these concepts, but in a very different language. Like asked a lot of questions. For example, did also they know what he meant when he used the word figure, but was it, whether it's not a figure. But I would say all of these concepts are extremely familiar in contemporary geometry, and people can spend thousands of pages in order to define to create the definitions that will allow them to recover the same properties. And they use language of continuous groups of topology and then category theory. So one of many questions I could ask. They don't use the language of metaphysics. Does that mean that these properties have ceased to be metaphysical now that they are governed by some explicit definitions and extended theories. Or are, one can say that they remain metaphysical even though people don't, mathematicians don't talk about them.
So for me, my understanding, I already had the discussion with Marco about metaphysical. So for me, what here also means by metaphysical is you look at a diagram. This diagram is no longer a diagram of ancient geometry. It has things that are pointer to imaginary objects. They relate, but they are not a construction. That's the points capital M prime, capital N prime. They are there, but since they are not on the conic, they are not a representation of the points of intersection. You have elements that you can draw, but are in fact imaginary, but they have a real thing that you can construct, even though they have imaginary relation. So you have different types of objects in this figure. And for me, what he means by metaphysics is what kind of elements we need for a figure to work generally with a figure considered as, I did not underline it, as a system of parts. A figure is a system of parts, and it can have different positions. And the issue is that if you introduce second as being either real or ideal, you bring under the same umbrella things that were considered to be different formally. And so, so the idea is the inventory of the various types of existence and non-existence for a figure. So this is what I understand he means by metaphysics here.
I had show a number of hands. I have Gemma and there were no. Well, so.
Thank you for the talk. I wondered in the republication of Poncelet's notebooks in the 1860s, I know he made many footnotes commenting on his publications, and I wonder if he commented at all on the difference between the 1818 text and the 1822 text. And then related to that, did Poncelet read von Stout, and was he convinced by the constructability of imaginary elements in von Stout through involutions as being a valid geometric construction?
So, thanks a lot for the question. So, in fact, as you know, we have the later publication. I have not emphasized it, but we have the later publication of Poncelet's notebooks. And we only have 2 notebooks that exist and which we now need to compare very, very, very accurately. Because in one of the notebooks we have, which dates to, I think, 1814, the 7th notebook, sorry if I remember the year with ±1. So in the 7th notebook, the expression, I think ideal chord or an expression or ideal second occurs. So, and we went to see the manuscript, and it is there. You know that the status of these documents is very problematic. We do not know exactly what these documents are, and we do not know how Poncelet really published his later texts. He changed orders and so on. So what does this expression, which in my analysis is introduced in 1820, what does it make? And this is a single occurrence in the 7th notebook. So this raises a huge question mark with respect to the exact nature of the publication in the notebook, or the exact nature of the notebook. Because if it were several occurrences of the same time, of the same type of the term ideal, it would be one thing. But here, all of a sudden, we have referring to nodes of geometry, and we do not know exactly what he meant by these nodes of geometry. So that's the first remark, that what these notebooks are is weird. That's the first thing. And no, I'm not aware of any comment you will make on the difference in the. In fact, the whole thing begins in the third notebook from the Metz period, and it comes really to the fourth notebook of the Metz period. I have not noted any remarks in the footnotes that would, and no, I'm not aware that he would comment on von Staud in this respect. Thank you for the question.
Questions?
It was fascinating. I want to understand more, if possible, about the notion of the physics, which was raised before.
The notion of what?
Metaphysical. Does he refer to some specific philosophical framework that he is kind of versed in, or is just like a non-expert generic use vague of the term metaphysical? Is there some specific Kantian background there? I'm curious if there's any indication.
Okay, so the first thing I can tell you is that Poncelet is anti-Kantian. However, what that means exactly is unclear, because it depends on what Kant was at the time in France. So he belongs to a circle in which you have Servois, you have Poncelet, and they wrote against Kant. So that's the first thing. Now, I think that I would need to study in the context what people meant by metaphysics in various contexts. Lagrange uses the term, Carnot uses the term. So I think it would be really interesting to put this in a context, but here, my understanding, again, what he's after is a complete table of all the metaphysical notion that belongs to the figurate magnitude. So this is a program whose answer, I'm sorry because I no longer have the arrows, so things go quite quickly. So the answer is this, because the same paragraph is placed before the statement of the call for a complete table of metaphysical notion of the magnitude, the same paragraph and the introduction of the two modes of non-existence. So I think that this table, which I'm drawing on the basis of what he says in 1822, this table is the result of this call for a metaphysical, a complete table of the metaphysical notion. So again, my interpretation is you can have several types of entities that enter into the making of a figure, somehow, in fact, in the same way as you can have two types of entities entering into the making of a number. It's the same in Kummer. You can have two types of entity, real and ideal, that can enter into the composition of a number. Here you have several kinds of entities that can enter into the making of a figure. And the problem is to identify the complete table of the type of entities entering in this figure. That's how I interpret this notion.
Back to the table, we have headings for the column, mode of non-existence.
No, wait a minute. This is me. Wait a minute, no. Okay, I will show you exactly what I mean. You see? You see?
Yeah.
Since just as one has in geometry names to express the various modes of existence that one wants to compare, like infinitely small and infinitely large, one must also have names to express those of non-existence.
So the tabular orientation is not in this text.
The tabular is mine.
And there's no indication of what would be the title of the columns. Sorry, not the columns, the rows.
No. Don't look for the meaning of the rows. But what is absolutely clear is that we have here an opposition between various modes of existence and various modes of non-existence. And in between, we have this call for tracing a faithful and complete table of all the metaphysical notions that belong to the figurate magnitude. So I think this, the term table is in this text.
So it seems conspicuous that there's nowhere on the table where you get finitely sized lengths or things in a figure. Is that just because the list is incomplete, or is there a reason that there's not, say, like a finitely long line?
Excuse me, can you repeat? You do not get what? I'm sorry.
So the table on the right-hand side in modes of existence, you have infinitely small and infinitely large. But what about just finitely large or something? Why is that not?
So in my view, you see, when already has like, so it's not that he's making, you're absolutely right that it's not the complete table, but he's making examples with things that he emphasizes, thanks to him, for me. He's making clear that he now considers these things as being extant, in contrast with the others that are not extant, but and so on. So I think that this is not a complete table, but here we have line.
It's essentially the same question, but I think that the line is not simply the answer for the things that if there is a parallel between the existence and the existence, it should be something also on the other side, between the imaginary idea. It is a table gives the impression that imaginary idea is extreme something. It's something that still not exists, but is not imaginary, it's not real, and it's something ordinary. And then on the other side, that I think is very small, maybe large, and something that is ordinary. So this life is a strange, because when I think something that exists, I do not think something that is more small and large. But again, that is not the first thing that I think about. So I don't know. It's not my. I do not know very well. But it seems to me quite strange to simply say that it doesn't make sense. It gives the impression that there is something more. So can I use here? I make an advantage. The last time that I make a question on this topic, I was much more critical. Now I advance the correction of what to say.
Good. It's good that when you understand, you are less critical. I'm sorry, it was easy. I'm really sorry. No, I'm sorry. It's a private joke between the two of us. No, I'm sorry. But I was looking for the French, in fact, which I have here. But I was looking. Okay, I will find the French later. You know, what is really striking for me is between 1819 and 1822, infinitely small and infinitely large have changed from modes of non-existence to modes of existence. This is what is striking for me here. And I think I need to understand better what happened. I think it's really extremely interesting. So why did they change? How did they change? can we find clues to understand this? This is what is really striking for me.
This is small that maybe.
Microphone, is it a follow-up?
Is this?
Yeah, follow-up.
Because the other questions,
You know, maybe for ordinary objects, we don't need to think about modes of existence. So, you know, the infinitely small and infinitely large, even though they exist, they have different strange modes of existence. So we have to somehow clarify or analyze their modes of existence. Ordinary objects, we don't. So maybe that's the simple way of omitting them. And to the note about the why the infinitely small and infinitely large became modes of existence, maybe the Cauchy, the appearance of Cauchy's textbooks could be the reason. That means that he uses them, but he clarified the concept.
Well, in fact, Cauchy wrote a report about a first version, or part of a first version of the 1822 treatise, which is the 1820 memoir that Poncelet submitted to the Academy of Science. And interestingly, Cauchy was very interested in ideal called ideal sequence, but not at all in the principle of continuity, which in fact, he only saw continuity, but he did not see the precision that were added after continuity. I'm still trying to find the French. It doesn't matter. So I think that perhaps Cauchy did not write about geometry in this respect. So I think that it would be difficult to interpret what he did as a solution for this.
Okay, thank you, Karin. It was really interesting. So still on the metaphysical side, let's say, of your talk, when you were commenting on that particular diagram with the ellipse and the proportions to ratio, yeah. So if I got the point, the metaphysical status of mathematical entities in general, like imaginary, depends on the specific figure, right? You are focusing on. Since I could, of course, there I could trace another ellipse for instance, on the right side, and consider that the imaginary element is, in this last case, line mn, because there is a particular proportion that I can build with this second figure that makes a line mn the imaginary one, right? So the general point I got from your discussion on this figure diagram was that the metaphysical status of specific mathematical entities really depends on the specific figure you are focusing on, which is, of course, something that was very, very curious to me, because usually when we talk about metaphysical status of something, well, does not depend on the specific, in this case, figure we are focusing on. But I don't know if my point was clear, but
yes, your point is very clear.
Okay,
so
thanks.
So the point is this: how many types of entities do we need to distinguish to describe the figure of a conic and a line? And so, or to describe a figure, but let me simply say, to describe a figure and a line, how many types of metaphysical entities do we need to distinguish? The answer that I'm giving, it's not in Poncelet, the answer is perhaps one should say 4. Exactly what we have seen. We have on the figure real elements. This is, for instance, when I draw the line MN here, we have points of intersection, we have a chord, they are real elements. By the way, there is something I want to emphasize strongly. There is no ideal per se. There is no imaginary per se. It is in the context of a figure that we have ideal elements, imaginary elements, real elements. And this is very important because to understand, it's exactly like in Kummer. We do not have ideal numbers per se. They are introduced or divised. They do not float. So this is really important because this will be a major change in what Dedekind will do. So in this case, so to describe the figure that can have different positions, I need to have real elements, I need to have ideal elements, and I need to have imaginary elements. And when I say real elements, should I put elements at infinity there or not? I think probably they belong to real elements. From what we have read, that they are modes of existence. So real elements contain all the things that are modes of existence. So this is the categories you must introduce to describe a figure. This is how I understand the metaphysical table. Is it clear?
Maybe a silly question. What's the difference between an imaginary element and the ideal element? Hilbert make the difference between real element and the ideal element. And according to your figure about the mode of existence and non-existence, what's the place of Hilbert's real element? Real elements should be exist, but real elements may maybe neither infinitely small nor infinitely large.
Thank you, thank you. So, okay, we will abstract from the figure, we will simply focus on the conic here, A, D, B, E, okay? We have a conic here, and a line, M, N, here, okay? So forget about this other conic, forget about this other conic, forget about that. If you draw a line here, M prime, N prime, perhaps I should put a larger figure here. If you draw this line, okay, this line has 2 points of intersection with this conic that I have named A, D, B, E. We have a conic, and this line has 2 points. So I cannot construct these 2 points because if I wanted to construct these 2 points, this line could not be a line because I would need somehow that this line crosses. This is that to which Ponce refers as imaginary. However, I can construct the line as a secant because as soon as I have, this diameter is conjugate to this direction. So MN is the direction and AB is a conjugate diameter. So as soon as I have any line parallel to the direction MN, I cross the diameter in a point which is real. And I can draw the line in the direction. So I have a construction to draw this line, despite the fact that its intersection with the ellipse are not real, they are imaginary. Is that clearer? Is that clearer?
Yeah.
So, for Hilbert, n prime would be ideal, as would be the points of the figures that are at infinity. So this is a different notion of ideal elements. As I have shown, for Hilbert, the points at infinity are ideal. The imaginary magnitudes are ideal. So this is, especially with respect to the point at infinity, we see that for Hilbert, they are ideal. And for Poncelet, they exist. They are not ideal. For the Poncelet after 1820, because for the Poncelet in 1818, we give the points at infinity, we give them an ideal existence, but it's only ideally that we grant them existence. So the Poncelet of 1818 is closer to the Hilbert of, I forgot which year, in that they both consider that the points at infinity have an ideal existence.
Maybe a last question.
Speak anachronistically about this sentence. From these ideas, we can see how we should go about tracing a faithful and complete table of all the metaphysical notions that belong to figure of magnitude, which is a fascinating sentence. And these days, there are several items in the mathematical review's classification system that correspond to precisely this sort of thing, and then you can draw a lineage of these practices back to Poncelet and to many other people. What one would say is that one would try to define the moduli space of some sort or other of all the objects of a certain kind, and then if you can, then you can do calculations with them, and the physicists are introducing objects of this kind that don't have any mathematically rigorous foundations. The mathematicians spent decades trying to do this. Is it possible to think about these things in that way, as Poncelet and as contemporary mathematicians and physicists do, or is this a fruitless exercise?
No, for me, what strikes me in what you just said is one can compute with them. And for me, it would be interesting to think about the part played by computation in these kinds of reflection, because computation introduces things on which you can rethink from this perspective, and the metaphysical question that Poncelet raises, this search for metaphysical notions, they are introduced because of computation. So the part played by computation there seems to me interesting to ponder. This is my first reaction.
And maybe this is the concluding note. So we thank Karim Chimlan. So we reconvene again after 2:30 after lunch, and I guess lunch will be served somewhere.
Yeah, so lunch is downstairs, but we're gonna go all together, so no problem, in 10 minutes. And we have plenty of time to chat in between. And at 2:30, the parallel session, some of which are downstairs, indicated.
There. But the problem was that you can see that is an extension of it.
Yes, I
So you can see, it was a bit difficult to.
No problem.